So we should get started, everybody. So I'd like to welcome you to another week of our Science and Cooking lecture series. And this week we're really very fortunate to have America's Test Kitchen here, who's going to show us some marvelous things. And also, actually, so I believe at the end they're going to have a book signing for a new book. So all of you know America's Test Kitchen, Cooks Illustrated, and all these things, but they just wrote this new book, which is called The Science of Good Cooking, which is really spectacular. And we've been using it in our class in various ways. The recipes in the book are really wonderful. Well, they're both good recipes to make, but they're also wonderful pedagogical examples to think about various aspects of cooking. And if you haven't seen it, you should all go look. But first, you have to put up with me for just a couple of minutes before you get to listen to them. So this is like, Dave and I have gotten used to being the warm-up act. So we're like the warm-up act. I'm going to be a very short warm-up act today because the reason that we have warm-up acts, is because that way there will always be some science at the beginning, so you can sort of see what's going on in the course. But these guys are really scientists too, and they know more about the science of cooking than we do, so therefore it seems appropriate that I sit down as quickly as possible. But so I'm going to do that. But first I'm going to tell you just a little bit about what we're doing in class this week. This is on Thursday. This is after you guys come tomorrow. We're going to be talking about microbes and food and cooking, and I just want to tell you one thing about that for you all to contemplate on your way home tonight. But first, we should thank our sponsors. So this lecture series is possible due to the generous support of many sponsors, among them Jose Andres' Think Food Group, the Alicia Foundation, both of whom really got us started in this, Zertoli Olive Oil, Whole Foods River Street donates foods for our labs, and so I hope you're all shopping at Whole Foods River Street, Taza Chocolate, Specialty Food, Boston, and Oya have all helped us out in various ways. So I was also told to tell you all one thing, which I messed up last time. I always mess things up for those of you who come week in and week out. But last time I messed up one thing which is important sometimes, and that is this. So on December 3rd, Farron Adria is here in this room. And the tickets are free, and and I think I might have said the date wrong, and I just want to make sure you get this right. If you want tickets, they're going to be available at the Harvard box office on Tuesday, November 27th, first come, first serve. So I just warn you, that's the only one that's actually ticketed in advance, but this one is ticketed in advance for anyone who's interested. Okay, so this week in class we're talking about microbes, and I just want to sort of discuss with you very quickly the growth of microbes. So this is not a microbe, that's a person. But as you know, one person gives rise to two persons. I mean, that happens sometimes. And then if you kill off, if you kill off the first person, then you can continue this process. 4 persons, 8 persons. I mean, it's sort of easier to kill off the persons before because then you're always just doubling the number of people and you don't have to count for the people that were there in the first place. And if you sort of ask, well, how many people are there? Then there's this sort of amazing thing that, as a function of generation number, the number of people goes up very quickly. So if n is the generation number, so if you're in the 6th generation of people, then the number of people there are in this model is 2 to the n, which is 2 to the 6th, which corresponds to 64 people, which doesn't sound like very many, so you're like, big deal, there are more than 64 people in this room. And there's an equation that goes with this, and actually you all have to clap, so that's our equation of the week. You have to clap. Because see, we clap here for our equation. If you have any equations, you can also ask them to clap. Right. I mean, they may or may not do it, but you can ask. That's one of the things we do. So anyway, so this is the thing, for some reason, people like Dave and I don't know why we do this. Instead of writing 2 to the n, we write exponential of kt, where k is given by that formula. We just like to make simple things complicated, and so we rewrite them in this way. But really, there's some time that it takes per generation, and the number is increasing with generation time. Now, so as you all know, this actually happens with people. So this is the population of the Earth as a function of time, and it's been going up. So this is a plot, from the beginning to the pyramids, and it's going up very rapidly. And it's sort of going up very rapidly for this reason, namely people are reproducing. It's the same as what I just said. And actually, if anyone is interested in this, I'll recommend one other good book. So today I'm giving you 2 great book recommendations. You should all read The Science of Good Cooking, and you should also read this book, How Many People Can the Earth Support? And this is basically the problem of, well, there's a finite amount of food on the Earth, and the people are growing exponentially, and so how many people can the Earth support? So why am I telling you all of this? So you'll see in a minute. So if you So if you look at the population, the doubling time of people that are sort of in the earth, this is a table that I copied from this book, then basically the amount of time it took for the population to double has gone down when the food quality got better. I mean, the better food there is to eat, then the more quickly people double. So that sort of makes sense. And so, and this is interesting for reasons that go well beyond this lecture, but the reason that it's interesting for cooking is the following, is that it turns out that microbes also grow exponentially, and microbes are very important for cooking. So if you start out with one bug, then one bug makes 2 bugs, which makes 4 bugs, and so on and so forth. And eventually, basically, you get enough microbes that your food goes bad. So has anyone done this experiment? You take a perfectly good piece of food and you put it on the counter, and then it goes bad? You've done this experiment? So, I mean, it's a ubiquitous experiment. It happens really quite frequently that you put it on the counter and it goes bad. And the reason that happens is all because of that equation that I showed you. And I'd just like to show you one simple calculation with it and scare you a little about food spoilage, and then I'm going to turn it over to these guys. Hopefully I won't make them sick before you start to cook. I'm sorry. I realize now this was probably a poor choice of introductions. I hope it's okay. I'm going to skip through very quickly the next slide. I'm not. You don't need to look at the next slide because these guys are going to cook good food. So I'm going to do this very quickly. Oh, okay. Okay, so you didn't have to look at that. And instead, we're just going through. So I just continuing this little calculation. This is sort of simple. We're up to 12 here, and there are now 4,096. But now they're not people; they're bacteria. And then I decided to keep going because I had a lot of time on my hands. And by generation 22nd, too, we're up to 4 million bacteria. So then I decided to ask myself the following simple little question, and this is just an interesting thing. Does anybody know how long it takes for a salmonella to divide? 20 minutes. Okay, so I decided to ask myself the question, how many salmonella, if I had one salmonella, and this is where I'm going to stop. Don't worry, it's not going to get any worse than this. If I had one salmonella, because we always like to do a calculation, so this calculation. So if you had one salmonella on your piece of food and you left it on the counter, then the question is, how many would you have 12 hours later? That's an interesting calculation. So,
50 million.
Say again?
50 million.
50 million, okay, so anyway, you might know it in your head. So it turns out that in 12 hours, you have 7 times 10 to the 10 bugs. And if each bug weighs 10 to the minus 10 grams, which is about right, then it turns out that that's 7 grams of bug. That's a lot of bug. And if you wait, what's even worse, and this is the one that I'm really going to just leave you with, if you wait 24 hours, then according to this calculation, you have 10 to the 11 grams of bug. That bug weighs more, that's more bug than there are people, the weight of everybody in this room. So there's something wrong with that calculation, but you get the idea. Okay, so with that, I'm sorry, this was really a bad introduction. Usually the introductions are appetizing, and I just messed this one up. It's, maybe I'll show you one more picture. So bugs are also good. They're used for making food. Here, I'll leave you with that. Bugs are good for making food. And so they're good for you. Like you can make chocolate with bugs, cheese with bugs, wine with bugs. So you should think about those sorts of things. And anyway, with that, I'd like to introduce Jack and Chris from America's Test Kitchen, who are going to tell us about the magic that they do. Thanks.
That was good.
Thank you, Michael. I'm really happy we're not, Dan, doing any turkey or chicken after that introduction. I mean, although, you probably all are aware that Thanksgiving is a very risky holiday for many reasons, but the number one risk is the one that, other than families turning on family members,
turning on each other,
would be the salmonella problem. Anyway, good evening. I'm here with my colleague, Dan Souza. I'm the editorial director at Cooks Illustrated Magazine and America's Test Kitchen. Despite Michael's very generous introduction calling me a scientist, I think that would be lying on my resume if I were to call myself a scientist. I don't consider myself a scientist. I'm perhaps an accidental scientist. I'm not actually a chef. Dan is a chef. I'm not a chef. I am a cook and a writer, and I have spent 25 years trying to understand the keys to successful home cooking. And along the way, I've deconstructed thousands and thousands of recipes into their basic formula, really trying to understand how food works and how cooking works at home. And I guess along the way, I have become an accidental chemist. And I really believe that if the average home cook thought a little bit more about science, that the recipes would be much more reliable and much more successful. Those of you know Cooks Illustrated. So this is our test kitchen. Here's Dan at work. I work with several dozen cooks, editors, writers. We have a 2,500 square foot test kitchen across the river in Brookline. And it's really a food lab slash test kitchen. And our goal is really simple. Collectively, we want to understand why recipes work and why they sometimes fail. What makes a cake rise and what makes a cake fall. What makes a steak juicy or what makes a steak dry. 3 years ago, I decided it was time to put everything that we had learned in 20 years and millions of dollars of ingredients being cooked into one book, sort of a best practices manual for the home cook. And put together a team that included 4 people, myself, Dan, who is an associate editor at Cooks Illustrated, and Dan was responsible for all of these really fabulous test kitchen experiments that he's going to bring a couple of those to life tonight. Dan, as I said, is actually a chef. He went to the Culinary Institute of America, the CIA. He graduated first in his class, which I'm always very impressed by, Dan.
It's not that very small classes. Very small.
Oh, is that how that worked?
Yeah,
was it class of 2?
Yeah. It is class of 2.
Dan has restaurant experience, like most of the people who work in our test kitchen. They are what I call restaurant refugees. Dan worked in Europe, he worked in New York, he worked in Boston. The third member, in addition to Dan and myself, is Molly Birnbaum, who's sitting here in the front. Molly, give a shout out. Molly's also an editor at Cooks Illustrated, and Molly was really the project editor of this book. She lived and breathed the book for 18 months. And Molly's an author of a really great book, Season to Taste: How I Lost My Sense of Smell and Found My Way. It's a really great personal inquiry into the loss of the sense of smell and how smell and taste are related to each other. It was shortlisted last year for an IACP award, which is the sort of Oscars of the cookbooks. So I heartily recommend that you guys check out Molly's book. The fourth member of the team, there was a scientist, Michael, on the team, so that we can be confident. Guy Crosby has been the science editor at America's Test Kitchen since 2005. And those of you who watch America's Test Kitchen, Guy is the scientist on air. Guy's got 30 years of experience. He's an organic chemist by training and has both worked in industry and has taught. So the focus of my talk tonight is science in the modern home kitchen. And I really want to talk about, I know most of the people who come here are chefs, and they're talking about the role of science in the restaurant kitchen. And I really want to talk about the role of science in the home kitchen, but I'm going to start by talking about restaurants. So my theory about the professional kitchen is that if you really look from a historical perspective, innovation is now the key to success in the modern American restaurant. But it really wasn't always that way. That if you look from the late 19th century to maybe the 1970s, the goal was all about making classic French recipes and not deviating from them. There was a right way to make sauce béarnaise, and there were lots of wrong ways. And the goal was to really just replicate these codified recipes in American restaurants. Things really began to change in the 70s. Lots of different influences, Nouvelle Cuisine in France, and the California-based chefs led by Alice Waters are probably the two most important things, putting an emphasis on lightening up of dishes, meaning getting rid of all of the fat in butter and cream and maybe replacing it with olive oil. An emphasis on really treating the ingredients right, and rather than covering them up with heavy sauces, letting those ingredients speak for themselves. And the blending of culinary traditions, so using Thai ingredients in classic French recipes. And I really thought that was the spark for what's really been a revolution in the last 40 years in restaurant cooking. And that in the last 2 or 3 decades, science has really played a really important role in the innovation that is going on in the restaurant world. I'd argue that in today's currency, an innovative dish is the most important thing. If you actually watch Top Chef Masters, there were many people who thought that the chef who won produced lower quality food, but it was more innovative than the chef who didn't win. And so I really feel like the world of professional kitchens, which is now really relying on science for a lot of the inspiration for this innovation, that success is basically, can I do something new and cool? So during this sort of period where all of the science has been influencing restaurant kitchens, science has had almost no impact in the home kitchen. The interesting thing is if you look back from a historical perspective at the first half of the 20th century, I would argue the two most important science trends were nutrition and home economics, and they actually had much more impact on the home cook than the restaurant cook. But all of the science trends that have been related to food in the last 40 years have really been focusing on a world apart from the average home cook's kitchen. So if you think about, does that really matter? Is there a role for science at home? And I do think that while home cooks are not really necessarily concerned with innovation, I think the average home cook is trying to replicate a recipe. They're trying to make a recipe out of a book, one they watched on television, and they're trying to execute it well. The reality is that they're really failing to meet what's actually a fairly limited goal. And I'm going to diagnose what I think the reasons for that problem are, and I'm going to propose that a little bit of science is the solution to what I would call the replication problem that many home cooks now seem to be having. So the first thing I want to talk about is what will seem really obvious is what I call the variability challenge. And so this is the first recipe I remember making on my own. It is the recipe from the back of the Toll House chocolate chip cookie. And, a lot of kids will still, both of my children have 2 teenagers. This is probably one of the first things they learn to make on their own. And what's hidden in there is 40 variables. And so the variables in any recipe will fall into 3 basic categories: ingredients, equipment, and technique. Now, none of this has actually changed. I mean, recipes have always had lots of variables in them. But my point is that there's lots of ways to fail. There are lots of variables. Something as simple, the first one, the protein content of flour. Well, of course, if you use bread flour, which has a much higher protein content than all-purpose, or if you use cake flour, which has a much lower, you can expect to fail. And if you use cake flour in a recipe that calls for all-purpose flour, I would argue you probably deserve to fail. What most people don't realize is that all-purpose flours vary, and that if you buy King Arthur, the protein content is 11.7%, and if you buy gold medal, it's 10.5%. So you ask, well, does that really matter? And I said, yes, it will matter in recipes where hydration is really important, because the higher the protein content, the more liquid is going to get sucked up. And it's also going to affect the gluten development, and gluten is what gives baked goods their chew. And so if Dan were to make the same recipe, same cookie with King Arthur, and I was going to make it with gold medal, there would probably be fairly subtle differences. Now, if it was a recipe where flour was the main ingredient, like a biscuit, those differences would be much larger. And so the point of this is there's lots of ways that things can go badly at home. A related part of the variability challenge is your equipment, even if you spent a lot of money on your Viking oven, is really, really, really inaccurate. So we sent home oven thermometers with 15 different people who work in the test kitchen. They took the same model that we had already tested, so we knew that they were accurate, put them in the middle of their oven, turned the oven on to 350, and 30 minutes later, they were supposed to write down what the temperature was. And as you can see, the variation ranged from 300 to 390 degrees. And of the 2 ovens that actually were accurate, one of them was a week old. Almost all of you have an inaccurate oven. I can guarantee you that, because I know that in the test kitchen, we have a professional person come in once a month to calibrate. I don't know, what do we have, 27 ovens, Dan? Some ridiculous number like that. And they're always out of calibration. And so, and this is where you think things are accurate. I think you probably all realize that medium-high on a cooktop here is going to be very different than medium-high on a gas cooktop. In addition to our equipment, our technique sometimes introduces an awful lot of variability. So this is another experiment that we ran in the test kitchen. We asked 18 test cooks to measure 1 cup of flour from the same canisters, all using the same method. There are 2 ways to measure flour. Either you dip the cup into the flour and sweep off the excess, or you spoon the flour in. Everyone was using the exact same method, the exact same flour, the exact same measuring cup. We then weighed the contents of the measuring cup, and we found a variability of 13%. We did the same test with liquid in a liquid measuring cup. Now, when people really messed this up and we asked them to put water in a dry measuring cup and flour in a liquid measuring cup, that variability doubled. And if you have 25% more flour or 25% less flour than you think you have some problems, and you're going to have a lot of recipe failure. So my point in all of this isn't to sort of, it's no surprise that there's variability. And professionals, when you see professional recipes, they always have weights because that's the best way to get around this. But of course, most home cooks don't weigh their ingredients. And in fact, historically, they haven't, and they haven't really had the kind of failure that the average home cook now has today. And my theory for that is one that I'm going to peg on my Italian grandmother. That my Italian grandmother knew intuitively what was going on when she cooked and could make adjustments. She cooked every day, which almost nobody in this room probably cooks every day. I think really importantly, she cooked only 40 or 50 dishes her entire life. And so it was the same 40 or 50 dishes that her mother cooked. It was probably the same 40 or 50 dishes that most of her neighbors who lived in her neighborhood in New York, who were mostly Italian Americans, were cooking. And so there was a lot of ability for her to deal with that variability that happens on a daily basis when you're in a home kitchen, just based on her tremendous experience. So, the reasons why I would say that the modern cook is so much less skilled and less successful in the home kitchen than my grandmother is certainly part of it is practice. We order way too much takeout. But part of the problem is just a culinary education perspective. And so I really think that there are 4 ways we learn to cook, and I think these are pretty obvious. Working with an expert, being able to watch an expert, getting your hands dirty and actually trying something, and being able to talk to somebody. And my argument is that the modes of learning how to cook have basically completely broken down. And that if you go back really any time in time before, let's say, the mid-19th century or the early 19th century, everybody learned by the apprentice mode. Maybe your mother wasn't much of an expert, and maybe there wasn't a lot of food for trial and error, but there was a lot of ability for a young cook to learn gradually with a lot of firsthand observation and a lot of assistance. With the rise of cookbooks as well as newspapers and eventually magazines in the 19th century, many people started to learn from a book. I'll call this the independent study mode. And it's a print-centric mode, obviously, and it really worked well for people who might have gotten a basic grounding in food from the apprentice mode, where they learned from their mother, but then they were able to go off on their own. And it really opened up the world of experts to you. The experts weren't necessarily in your kitchen, but they were really, really, really good experts. And a lot of the really good experts, like Julia Child, and that's Julie Powell cooking from her book, could really even anticipate the questions that somebody was going to ask and answer them in advance. And there wasn't really quite a sort of one-on-one dialogue. Well, it was one-on-one, you were by yourself, but Julia Child could be in the kitchen with you. Of course, the rise of television, as with many things, has changed everything. We're now in what I would call the passive observer mode. And we have access to experts, but there's really not a whole lot of instruction. And while there's a lot of observation, there's really not a whole lot of trial and error going on while you're sitting on the couch or while you're on a plane watching the Food Network. And there's really nobody who can answer your questions. So the way we learn to cook is really broken, which I think explains why skills are decreasing. But the funny thing is that expectations are actually rising. My grandmother was really happy making the same 40 dishes really well her entire life. The modern cook wants to make tiramisu, but also wants to make tamales, pad thai, and pozole. And this, has really is a factor of the key things that have changed in the last generation or two, which is we've gone from really relying strictly on local ingredients to now we can get anything in the world, a limited number of recipes to, tens of thousands, millions of recipes that are on the internet, to single shared traditions in communities, to now many traditions. And your neighbor is no way making the same food that you're making. If you live here in Cambridge on any block, there are hundreds of different traditions probably that are being followed on that one block. And so many people are now looking online, to find like-minded cooks. But the reality is that a lot of online recipes are just awful. The details are sketchy, and the results are not really reliable. I mean, if you think about allrecipes.com and compare that to Julia Child, it's fairly depressing. But there is a solution, and the solution is a quick course in chemistry. I think really science can provide a framework for learning to cook, and that can provide the framework for understanding the variations that are going on in your kitchen. And if you have some clue as to what's going on, you can then make the adjustments that somebody who might be cooking their entire life will have figured out over the course of an entire life. And so, the reason why I think science is the answer is because the reality is you are a chemist every time you're in your kitchen. There are three basic ways to initiate a chemical reaction. You can use mechanical force, you can use heat, or you can combine ingredients. Now, most recipes involve all three of these processes happening probably simultaneously, but I'm going to try to tease them apart in a way that's a little simpler, and then I'll put them back together. The first two, mechanical force and heat, can actually apply to a single ingredient. Obviously, combining ingredients involves at least two, probably more ingredients. But let me start with the mechanical force. So, what I mean by mechanical force are physical changes to the cellular structure that causes a chemical reaction. And that force can be supplied by a knife, a whisk, a food processor, or a citrus reamer. A good example here is what happens to oranges when you juice fresh oranges. Now, fresh oranges contain a compound that when the cell structure is ruptured, will combine with other compounds to form something called limonene, and it's what makes fresh orange juice bitter. Now, when you buy Tropicana in the supermarket, it's been pasteurized, and the heat will kill the bitter compounds, and so you do not get a ridiculously bitter glass of orange juice, at least you shouldn't. But in fresh orange juice, that reaction will continue kind of indefinitely. And we've actually run some experiments where we've compared fresh squeezed orange juice that was squeezed 4 hours ago versus actual fresh squeezed orange juice. And it's totally apparent to everyone that the older the juice is, the more bitter it is, and that it's very easy to basically taste that chemical reaction that was started by something as simple as a citrus reamer being used to squeeze the juice. The knife, of course, is probably the most familiar way that mechanical force is going to be used by the home cook. And the interesting thing is that many, many foods with strong flavors, think about like blue cheese or basil, actually have a lot of aroma. But garlic and onions really have very, very little aroma. I mean, no one cries at the supermarket when they're shopping for onions. Well, at least they shouldn't be crying when they're shopping for onions. But the minute you slice into that onion, the aroma is overpowering, and the tears are going to flow. And you've started a chemical reaction. And as this slide indicates, you basically are allowing things that nature has kept separate to, once you've ruptured the cell structure, changed the cell structure, things that are now able to combine, and they can form new flavor compounds. Now, of course, this is a good thing. In addition to perhaps making you cry, it's what develops flavor. And that, in fact, now garlic and onions, the chemicals are different, but the processes are exactly the same. And that when you are slicing into garlic, you're creating a compound called allicin. And it's what gives garlic its scent, its flavor. And the more you slice into the garlic, the more allicin is developed and more flavor. So for instance, if you mince garlic and then use that in a recipe, that garlic will add a lot more flavor than sliced garlic because you've caused more cellular damage, and therefore you have caused a greater chemical reaction it's created more flavor compounds. In onions, the process is exactly the same. You are creating compounds called thiosulfonates, and you're also creating compounds, of course, that make you cry. Now, you can sort of stop those compounds in the tracks, again, by heat, as with the orange juice and the pasteurization process that sort of stops that chemical reaction. The compounds that are created when you slice into an onion, really the negative reaction stops and the positive reaction begins once you start cooking it. And those compounds that are created that are causing you to cry, that you can smell, are the same compounds that are creating a French onion soup that has a tremendous depth of flavor. One more example is we ran a really great test showing how the mixing of garlic with another ingredient can make a huge difference in something as simple as a salad dressing. And so it turns out that in addition to heat, you can stop the reaction that is caused when you slice into garlic with acids, with lemon juice. And so we made 3 different vinaigrettes. In one, we added the grated garlic directly to the prepared vinaigrette. In another, we added the grated garlic directly to lemon juice and let that sit for 10 minutes. And a third, we just let the garlic sit for 10 minutes, and then we added it to the vinaigrette. And it was a really sort of nice continuum that the garlic that was added immediately to the lemon juice had the sort of mildest flavor. The garlic that was added to the vinaigrette was next, and that the garlic that was added after sitting for 10 minutes to the vinaigrette was just inedible. I mean, the dressing was just way too sharp and way too overpowering. And so, the trick when you're using mechanical force is to understand how much mechanical force and then how to stop it, which is, I think, a segue for you, Dan.
That was a good segue. Yeah,
okay.
That was good. It was good. All right, so I'm going to do just a quick little experiment here. When Jack talks about enzymatic activity, it's often a good thing. We don't get the flavor of garlic or onion until we cut it, but that's not always the case. So I'm going to put together something that folks at home probably make quite a bit, and that's a basil pesto. So I got all the ingredients for it here. This is some fresh basil. I've got pine nuts, some Parmesan cheese, and some olive oil. I'm sure when you guys make stuff at home, you also have everything completely measured out like that and just dump it in the same way. All right, so I'm going to put this on. I'm just going to buzz it for about 45 seconds, bring everything together. Give it a quick scrape down. All right. So, as you can see, as I take this out, this is nice bright green pesto. I'm going to make sure I get the camera over there. Can we see that? So basil has a lot of chlorophyll in it, and what we're doing is by chopping it up, we're letting all of that chlorophyll out, so you can see that nice bright green color. So this looks good right now. We're going to leave this. We're going to hop back to Jack, and we're going to come back and take a look at it in just a couple of minutes. We'll see if anything changes.
It's going to reveal itself.
It's going to reveal itself. This one is a slow. We have to wait for this one. This is slow. And it's like watching paint dry, probably, so Jack's going to talk about some other stuff in the meantime.
I hope it's a little faster than paint drying.
It's a little faster than paint drying. It is.
So we talked about the first way to begin a chemical reaction home, which is mechanical force. And the pesto, which we'll come back to, is an example of that. Mm-hmm. Second way is heat. And so, let's start with something simple, green vegetables. When overcooked, you can smell the chemical reaction occurring. You can smell and see that bright green and tender eventually becomes mushy and dull, and that the green vegetables, as with the basil, have chlorophyll, which is a complex molecule that contains a magnesium ion at the center. And when the chlorophyll is heated, it loses this magnesium ion, and the results are that that bright green color fades, and you get the dull olive green hue that's associated with the green bean casserole that many of us will probably be forced to eat next week at Thanksgiving. Now, heat doesn't always have to be a bad thing. When it comes to spices, heat actually brings the aromatic oils in the spices to the surface, which contributes to a much stronger flavor. Heat can also cause the Maillard reaction, the browning reaction between the sugars and the amino acids in certain spices, especially cumin. You can actually, if you sort of toast cumin or a lot of other spices, you can sort of see the color change if it's in the pan by itself. And the changing color is also a sign that the flavor is changing. Now, a lot of spices and a lot of herbs have what either you can have fat-soluble or water-soluble flavor compounds. Most of the compounds that we appreciate in spices and herbs are fat-soluble. Not all of them, but most of them. And here's a really interesting experiment where we took 50 grams of each pepper flakes and thyme, steeped them in 100 grams of canola oil for one sample, 100 grams of water for the other, brought it to 200 degrees, kept it there for 20 minutes, strained it, and then tried to measure the flavor compounds. And so for the pepper flakes, what we're measuring is capsaicin, which is what gives the heat. And that's Scoville heat units is SHU. And you see that the oil was able to extract about twice as much flavor, basically, at least of this one compound, the capsaicin, as the water. Now, at the time, we were measuring thymol, and you see there the difference is really quite stark. The takeaway here is that when you're cooking with spices, if they contain fat-soluble flavor compounds, you want them to be seeing some oil at some point. In addition to this experiment where we were keeping the temperature constant, of course, oil is going to get much hotter. Water is going to stay at 212 degrees, and oil is probably on your stovetop going to get to 350. So in addition to the inherent advantages when the temperature is constant, when the temperature of the oil gets up to 300 or 400 degrees, you can really get a lot more flavor extraction. And so in the test kitchen when we're developing recipes, this is the kind of fact that we will then use in order, for instance, to make a better chili. And that a lot of chili recipes dump the spices into the pot once the tomatoes, the beer, or the broth are already in. Well, they're not really maximizing the flavor of those spices. And so whenever we're cooking with spices, pretty much always, we will add them when there's not liquid but fat in the pan. And so for a typical recipe that is sauteing onions and garlic, we will then add the spices at that point where the aromatics are cooked, but before the liquid ingredients go in order to get the maximum flavor out of those ingredients. So I love this example of heat. You're going to be like, the transition here is not going to be immediately apparent. But this is a great example of how heat can affect a chemical change. Now, everybody who's made an apple pie has had this problem, what we call the gaping crust. And so the crust will set up, and the apples, as they cook, will cook down. And what you're left with is this huge chasm, which makes it really, really difficult to slice the pie. I mean, it's not just unattractive. Functionally, the top crust basically falls apart when you go to slice it. They must have used a saw or something in the test kitchen to separate half of the pie here. And so, we thought in the test kitchen we would solve the problem by pre-cooking the apples before we put them into the raw pie, with the pie plate that's got the bottom crust, and then add cooked apples which had cooled, and then put the top crust on. Now, we had expected to do this, that when we did this, we would be trading off some texture, and that the final pie would actually be pretty mushy, more like applesauce. And we were really surprised when we found out, test after test, that the filling actually seemed firmer when we used cooked apples than when we used raw apples. This makes really absolutely no sense. So this is a case where we would call in Guy Crosby, the one real scientist who works in the kitchen, and he's like, Guy, what on earth is going on? We've repeated this mistake numerous times. And it turns out that when apples are heated and heated gently, the pectin that glues the cells together is converted to a more heat-stable form that prevents the apples from becoming mushy. And that basically, if the apples are held at about 140 degrees, that the enzyme pectin methylesterase causes the pectin to link with calcium ions that are present inside the cell structure and basically prevents any further degradation of texture. And so when we cook the apples in a skillet, which gets much hotter, we found that we got no protection from pre-cooking the apples that way, and that the final apples are really quite mushy when they were pre-cooked in a skillet. But when we pre-cook them in a Dutch oven with a lid on, where the temperature is really much more gentle than it's going to be in an open skillet, the temperature ended up being actually near this 140 degrees, and we ended up with these pre-cooked apples that when we put the top dough on, they weren't going to shrink anymore, so they were sort of flush in the final pie with the top dough, and that they were still relatively firm, even though they were cooked for, yet again, another hour inside the pie dough in the oven. And so this is like an unexpected way that heat can sort of cause a positive chemical reaction. So
That's also a good segue.
Okay, that's a good segue?
Yeah, that's a good one, yeah. So if we take another look at this, and I don't know if we can scoot the camera over to take a look. And is that showing up on there? Okay, cool. So that, you can see that that's changed a little bit. Now I have this other pesto for comparison. And the one on my right, I actually made this morning. So it's been sitting here for quite a few hours. And does anyone have any idea what I did to the one on the right? Yeah, who said that? Blanch the leaves. Yeah, that's good. That's right. That's exactly what I did. So basically, with this basil, I blanched it in boiling water for about 30 seconds and then shocked it in ice water. And now what that does is the enzyme that's responsible for turning this chlorophyll dark, and this will eventually, this will turn black in probably another hour or so. Not a very attractive color. The enzyme that's responsible is called polyphenol oxidase. That's the same thing that turns potatoes and apples brown. But heat can deactivate it. So that quick blanching step deactivates it. And now this has been out for probably a day at this color, but I've held it like this probably for a week, and it stays the exact same color. It's a little bit weird looking because it stays green for that long. But I think the big takeaway here is that if you're making a small batch of pesto just for your pasta dinner on like a Tuesday night, then you probably wouldn't end up doing this. But it's like August and you have a huge batch of basil pesto you want to make. It's a quick step that you can take that in the end is going to keep it a lot prettier for when you serve it. So I think that's an easy takeaway.
Yeah, and it's a lot better. I grew up, my grandmother would add vitamin C because the acid can actually work, but then you can taste the vitamin C in the pesto.
Right. Well, and someone mentioned lemon juice too, and lemon juice does have some effect. It's not as effective as doing this, as well as garlic. If you have garlic in your pesto, that allicin compound that you talked about can have some effect, but blanching is by far the most effective.
So continuing on with the theme about heat, of course, probably the thing that we're most familiar with cooking would be meat. Want to talk a little bit about like when you order a steak out at a really good steakhouse, why is it so good, and why is the steak that you get at the supermarket usually kind of mediocre? One of the main reasons, besides the skill of the people who are cooking, is probably that steak was dry aged. And they are basically hanging the meat or letting it rest in a humid refrigerator that's probably somewhere between 32 and 40 degrees. And during that time, besides evaporation, which is sort of concentrating flavor compounds, there's actually enzymes in the meat that are breaking down the muscle proteins and are making that steak much more tender. There are two really important enzymes in meat, calpains and cathepsins. The calpains break down the proteins that hold the muscle fibers sort of in place. And the cathepsins break apart sort of filaments and the supporting molecules and also break down the collagen that's in the connective tissue. And the overall result is if a steak spends 3 or 4 weeks being dry aged, you end up not only with the formation of all these flavorful amino acids and peptides, but your muscle fiber is broken down and it's much, much more tender. And that basically dry aging equals tender texture and more flavor. Now, the rate at which those enzymes do the work is governed by temperature. And at 32 or 35 degrees, it's actually working very, very slowly, which is why dry aging a steak for a day or two in your refrigerator isn't really going to work. And your refrigerator is much too dry to be able to do it for 30 days, for instance. And it needs to be in a very humid environment in these specially controlled environments that they have in restaurants. The rate, though, at which this enzyme works heats up, so to speak, speeds up. And that basically until you get to, in this illustration, anywhere below 122 degrees, the enzyme is basically shaving apart and breaking down those proteins. And that at 60 degrees, it's faster than at 40. At 80, it's faster than 60, and so on. And then it basically, once it shuts off at 122 degrees. So we figured out in the test kitchen that if you didn't want to dry age meat, which isn't really practical at home, could you get these enzymes to work their magic by the way that you were actually cooking that roast? And we developed a recipe for a slow roasted beef that used a boneless eye round, which is a cheap, not very good cut of meat that's from the rump. And it's not really gnarly. I mean, it's not like something like that's really tough, but it's not terribly tender either. And so we did a couple things to this roast in order to greatly improve its texture. We first salted it overnight. The salt, besides providing seasoning, is actually breaking down some of the muscle proteins and begins that process a little bit. The next step was to brown the roast so that we could develop some flavor, because as you will see, we then put it in a 225-degree oven and cooked it in a 225-degree oven, which of course we're getting absolutely no browning in that oven. And we cooked it until the internal temperature of the roast got to 115 degrees, which takes about an hour and a half. And at that point, we turned off the oven, because what we were really trying to do is to get it to sort of crawl over the finish line. I mean, the finish line for a piece of meat that you want medium rare is 130 degrees. And so what we were trying to do is to get it to spend the absolute most amount of time it could below 122 degrees in order to maximize this tenderizing effect of the sort of the enzymes that are in the meat. And so this total cooking time with the hour and a half at 225, another 50 minutes in the turned off oven, if you would have just thrown that 4-pound roast in a 375 oven, it probably would have been done in less than an hour. And the point is that we really felt like we were convinced you could taste the difference, and that the roast that had been cooked in the super low oven was much more tender. But one of the things that Dan worked on the last 2 years was we wanted to prove it. That we do a lot of sensory evaluation. And our process is that we'll have sample A and sample B. No one will know what sample A and sample B is, and there'll be 8, 10, 12, 15 people come in and vote. And usually, if it's 13-1, you have a sense that you've got good data, but it's not terribly scientific. So Dan came up with a way of sort of proving to us in a way that's a little different what it is that was happening and that it was actually happening.
Yeah, okay, so if this was like the most normal experiment, this is probably the weirdest one that I'll do tonight. So, we have a test kitchen. It's not a laboratory. We don't have, really sophisticated equipment to test things. So sometimes we kind of think out of the box and have to do something a little bit different. So for this, we did get to use a little bit of cool technique and a cool instrument. But basically what we did is we've had a boneless ribeye roast. So we cut that in half into 2 really big steaks. We vacuum sealed them. We don't have a cryovac machine, but we vacuum sealed them. So it's already getting kind of cool. We're sealing things in plastic. Then we used a low temperature water bath. So we have a sous vide supreme that we use. And so we set it for 120 degrees. Now, as Jack mentioned, that 122 cutoff is where those enzymes deactivate. So they're not doing that nice snipping. They're not tenderizing the meat anymore. But the closer you get to that temperature without going over, that's like Price is Right? Where the closer you can get without going over. So, but once you go over, it's no good. So you got to get up to that point, and it happens very fast at that temperature. So we had these 2 steaks vacuum sealed. One went into the sous vide supreme for 48 hours, like a full 2 days. At 120, which is rare. If we know, rare steak is cooked to 120. And then for the other steak, we simply put it in for about an hour and a half, just until the internal temperature was 120. So they're both cooked at the exact same temperature. One has spent 48 hours there, the other has spent maybe 2 hours there. After that, we took the steaks out. We cut them into essentially pieces that you would most likely eat. So they're cross-grained cuts, about 1/4 of an inch thick. And then I went online and I bought sinkers, lead sinkers that are like 2 pounds each, from this great company called Grateful Lead down in Florida. And they were awesome to deal with. And they were like, "What are you doing with these things?" Because I ordered a lot of different sizes and weights, and I was like, "Oh, I'm tying like meat to them and doing all this stuff." So he thought I was crazy. But so basically, I have these strips of meat, and I've tied with butcher's twine these 2-pound weights to them, and I'm going to pick them up with tongs, and we're just going to see what happens. Now, sometimes it usually happens pretty fast. You know, this is the kind of experiment where I have to do it in order to see what happens. So we're just going to experience this together. So I'm going to try and do it at the same time. And I'm basically holding the top of each one here with some tongs. You guys as excited as I am? This is going to be pretty good. I've never done both at the same time because I usually don't have to, but it seems like the drama would be better for that. So. All right, so I'm going to pick them up, and we're going to see what happens. Should I say? Yeah, so the one on my right is the 48-hour cooked, but it's 120, so it's still a rare steak. If anyone's had a rare steak, you know that it's not that tender, right? Like, it's a little bit chewy. Okay, so let's see what happens. Ready? Can you see? It's looking like it's going to go. I could shake them both. I'm going to shake them both, so it still counts, right? All right, there we go. This one's still holding up. All right, there we go. So we kept it scientific. We're shaking them both. So it's kind of a crazy experiment. These have also been air drying out here, like turning into jerky, basically, while we've all been talking. So that's probably not helping things. But this is an extreme example, but it definitely shows us that something is happening. And if you eat a rare steak, you know that it's pretty tough. I wouldn't ask anyone to eat this because it's been sitting at 120 for 2 days, but it's indeed a lot more tender. And what this is showing us is those enzymes are really active at that point. And so we're basically dry aging meat. When we do it in our home oven, kind of this modified method that Jack talked about, it's happening. It's happening a lot quicker because we're using warmer temperatures. But you can turn meat that isn't as tender into something that's a lot better.
Great. I can't believe you pulled that one off, Dan. I'm impressed.
Yeah, I know. It's pretty good.
So in addition to heat and mechanical force, the third way that you can basically start a chemical reaction in the kitchen is really the most obvious, which is to start combining ingredients. And I want to talk about marinades. So this is this greatly misunderstood phenomenon of what you should be doing when you're marinating meat. Most people think, it's a bottle of Italian dressing, and it is the acidic ingredient, the vinegar, the lemon juice, or a really wine heavy marinade, and that's somehow doing the trick. And the reality is that it's making matters much, much worse. A protein molecule typically contains positive and negative charges. And generally, they're more positive or more negative charges, which causes the protein molecules to repel each other. And they sort of stay far apart. But if these charges balance each other out, you reach something called the isoelectric point. And the proteins end up sort of packing close together and squeeze out liquid. And the result is a very dry piece of meat. Now, when you're working with chicken, it's actually slightly acidic. The pH is somewhere between 6.0 and 6.5. And the isoelectric point for muscle protein occurs at about 5.2. And so if you put chicken in, or any muscle protein in a highly acidic marinade, you can actually lower the pH to the point where you are causing the moisture to be squeezed out of the steak, so to speak. And that you may get some mushiness on the exterior, which can seem like it's tenderness, but that overall, because you've squeezed out the liquid, that the meat, the chicken, whatever it is much drier, and it seems to be much tougher. And so all of these marinades that rely on acidic ingredients are absolute failures. If you really want lemon with your marinated chicken kebabs, serve the lemon wedges at the table, but do not put it in the marinade. What you should be putting in is salt. We find that super salty marinades that are either made with salt itself or with a salty ingredient like soy sauce will make meat juicier. And since we perceive juicy meat to be tender meat, if what you're really trying to do with your marinade is to somehow make that meat more palatable, you should be using salt. I mean, what you're basically doing is brining the meat. You're changing the structure of the muscle proteins so that when they're cooked, they can hold on to more of their natural water. Meat's usually, it's about 75% water, and the goal in cooking any meat is to minimize that moisture loss. In addition to salt, most of the marinades that we develop in the test kitchen have fat in them because most of the ingredients that you're putting in your marinade, think back to the spices and herbs, have fat-soluble flavor compounds. Now, they're not going to get into the meat, but they will, if you've got some oil in the marinade, sort of cover the exterior of the meat so that you end up with at least the spices clinging to the outside of the meat. So we've talked about these three ways. I want to now go through three case studies that will perhaps bring this to life in real recipes. The first of these case studies is going to be about eggs. Dan did a lot of work with a lot of fun tests with eggs.
There's a lot of good stuff about eggs.
And I want to begin by looking at whipping of egg whites and what happens when you whip egg whites. So the whipping action is creating these air bubbles in the egg whites, as you can see there, air bubbles. And the whisk is causing the proteins in the egg whites to sort of unfold and bond to each other. And they're forming a mesh-like network that's basically coating and reinforcing those air bubbles. And this is what's allowing the phase change, and that liquid egg whites will turn into a foam. But egg whites are 90% water, and the foam is very unstable. Gravity is basically going to encourage the liquid portion to come out of the egg whites and for the foam to disintegrate and to lose its structure. Now, there are ingredients that you can add to the whites, though, as you're beating them that will make them more stable. Cream of tartar, which Dan is going to talk about in a minute, is one. Also sugar and cornstarch, because they can make the egg foam more stable because they have water-attracting properties and can sort of slow down the natural separation of the water from the foam. But Dan's going to talk a little bit more about his experiment here.
All right. Well, so we've got two experiments for egg whites, and the first one is some audience participation. Do you guys want to come up here? So I've got 2 bowls of egg whites. There's 2 whites in each and 2 pre-selected volunteers. They're not, I don't know their whipping skills, so it's not.
Yeah, this is like Iron Chef.
Not like
I'm
not like I'm setting up. So this is yours, and this is yours. So basically just kind of, whipping moderate pace. We're trying to get to like kind of soft to stiff peaks. Get some air incorporated in there. So while you guys are doing that, and I don't know, it shouldn't take too long. It should be good. So this experiment here, which is already set up, I did this about an hour ago. And as Jack was saying, you can add different ingredients to egg whites to help stabilize them. And I've done just that here. So I whipped these egg whites about an hour ago. On the right, you added a 1/4 teaspoon of cream of tartar to it. So what cream of tartar does in egg whites is it actually changes the electrical charge on the protein. So it's a little bit counterintuitive, but the proteins are actually less likely to bond together. So it takes longer to form a foam when you have cream of tartar involved, but you actually get a more stable foam because of that. And you can see the difference here. I'm getting more liquid out of the one that's unstabilized, and there's a very different appearance to both of them. You have a lot smaller bubbles here, and so this is better, cream of tartar. So
Dan, you didn't introduce me to our 2 participants.
I'm sorry. So we've got Ezra.
Okay.
And I've forgotten your name. Marisa.
All
Ezra
right.
and Marisa. And I didn't know what their skills were before, but it looks like Ezra's a lot better at it.
So you're hired.
Yeah. No, all right, so it's actually a setup. So basically what I did, I don't know, can you see it on the camera? We can see the difference.
We promise you these nice audience members are not plants. This has nothing to do with skill level.
You seem to be doing fine. It just didn't work. So basically, the difference here is I sprayed this bowl just briefly with a little bit of cooking spray before I gave it to you, so I totally set you up. It's not your fault. Whereas this one is just the egg whites. And so, thank you guys. You guys can sit down. I wanna.
Thank you.
So it's just a light coating of cooking spray, and I think this is a great demonstration to teach people about when you're going to whip egg whites and you get a little bit of yolk in there when you're separating your eggs because they're not cold enough, and you get that yolk in there. Just start over. Just don't even try and whip at that point. So what the fat does is it actually coats a lot of those proteins so that they don't interact at all, which isn't a good thing. And then when you actually form the foam, they take up a lot of space on the bubbles, and that weakens the entire network. So we could let them whip kind of all day. This would break down after it's overbeaten, but this wouldn't really get much beyond this point. So that's the lesson there.
Yeah, and a really sort of interesting practical thing is that if you try to whip egg whites in plastic bowls are really, really hard to get clean, especially if you're not using a dishwasher. They always seem to have a little film of oil in them. And so one of the things we tell people is to always use a glass or a metal bowl, not a plastic bowl, because odds are there's a little bit of oil left on that plastic bowl, and that Tupperware is not meant for whisking egg whites.
That's good. That's a good point. Yep.
Sticking with eggs, so heat and the role of fat in coagulation. So this is another example of Dan's sinker weights.
Oh yeah, they're there.
Yeah, you like this one?
Yeah.
So the same thing is happening in an omelet, which is used with whole eggs, which is that the egg proteins are unfolding and forming a lattice gel, and that's turning the liquid whole eggs into a solid or a semi-solid, and it depends on how long you've cooked your omelet, that you can pick up with a fork. And this is a really great example. One of the things we did was we wanted to see what the role of fat was when you're cooking eggs. And so for this experiment, the sample on the right had teeny cubes of cold butter added to the omelet mixture before it went into the pan. And the sample on the left, that the pan, of course, it was a nonstick skillet, had a little bit of fat in it, but there was no fat that was mixed with the eggs before they went in. And, again, we were doing sensory analysis, and it was very clear that one was much more tender, which in the case of an omelet, you actually want tenderness, not toughness. But this brought it to life. We said, well, we're going to put, these are 2-pound, I think, Dan, they were 2-pound weights that were on these.
2 pound
and obviously,
yep.
The very, very sturdy omelet on the right is sturdy enough that you can put a 2-pound sinker weight on it, and it's not a particularly pleasant eating experience. This one, once you get rid of the sinker weight, is a particularly pleasant experience. And so the takeaway here is that if you're cooking eggs, you need fat. Dan did a great recipe last year at Cooks Illustrated for scrambled eggs. And upping the number of yolks, which increases the amount of fat, using half and half rather than skim milk or milk, gets more fat in there, which is going to sort of coat that protein network. It's going to sort of prevent the squeezing out of liquid, because what happens is you are cooking the eggs, that it's continuing that network to get tighter and tighter, and what you can do is sort of squeeze out the liquid. I mean, if you've ever made a sort of weepy batch of scrambled eggs that have sort of tough little turds in them, not curds at that point, they've sort of transitioned, is you've cooked the water out of the eggs, basically,
right.
And that's why they are weeped, and you overcook them. By adding some fat, you can give yourself a little bit more cushion there, and you can cook them long enough. So for instance, if you actually want an omelet that's not completely runny, you can get it so that it's cooked through, but it's not going to be tough. One more egg thing, because eggs are the most amazing ingredient, is the effect of acids and starches. And so, everybody knows that if you cook eggs, they will change into, and eventually they will coagulate and form curds. But if you use acids like lemon juice, like in lemon curd, or you use starches, like pastry cream usually has cornstarch or flour in it, you can actually boil the mixture, the pastry cream or the lemon curd, without getting bits of, sort of scrambled eggs in it. And this is a simple experiment where we made pastry cream with and without starch. Much like the fat, in this case, it's the amylose that's in the starch, which is sort of coating the egg structure and preventing those little bits of scrambled egg, like you see on the left, from forming in the one that was on the right, and that they, in this case, they were both boiled. And the reason why this is really important is because in order to get pastry cream that's thick enough to slice through, which is important if you're going to be using that pastry cream in a tart, you really do need to get the maximum thickening power of the eggs, which means you want to boil the eggs. But if you boil the eggs and you don't add some sort of protection, you get really thick scrambled eggs, basically. And this, of course, the starch prevents that from occurring. So the next case study I wanted to talk about was bread. And I think the appeal of bread is that, of course, this is about the oldest chemistry people have done at home, and that it's really complex, but it's also actually quite simple because there's so few ingredients involved. And so at very basis is that the process begins with hydration. And so when you start on the left, you have these starch granules surrounded by protein strands that are basically inert until you add the water. And that when you add water, the wheat proteins come to life. And you are seeing that they are changing shape. The protein molecules are sort of unwinding, and the loosely coiled glutenin and the more tightly wound gliadin are beginning to sort of link up and form these long elastic chains, which we call gluten, which is what gives bread its structure and its chew, and gives all baked goods that are made with flour their structure. Now, when you add yeast to the mixture, I mean, if you add water, things have changed, but you now just have basically some weird porridge. But if you add yeast to the mixture, it reacts with the sugars produced by the breakdown of the starches to create carbon dioxide. And as that gluten network is formed by the mixture of the water and the flour, it relaxes and expands and traps that CO2, and that the yeast is also producing all these flavor compounds, especially ethyl alcohol, which is what gives bread dough that characteristic aroma that when you're making bread, you can smell it rising. Now, in general, in test kitchen, we find that you get more flavorful breads when you're working with yeast when you slow down the process. And there are basically two ways to do this. You can either use something called a pre-ferment. A sponge is an example. Sourdough starter would be another. A sponge is basically a portion of the flour, the water, and the yeast that are mixed together and left out on the counter for 6-8 hours. You then come back and you add the remaining flour, the remaining water, and the remaining yeast. And what's really happening during this time is that the long carbohydrate chains and the starches and the polysaccharides that are in the flour are breaking down into sugars and acids and alcohols with flavor. And that by starting a portion of the yeast and the water and the flour, that reaction is taking much longer period of time. And that you end up with more flavor. In addition, sort of a second way besides a pre-ferment or a sponge is to use cool fermentation. And so that's to mix all the ingredients together, but to slow down the pace of the reaction by letting the dough rise in the refrigerator. Professionals will call this retarding the dough, retardation. And you're basically getting more of the good flavor development by stretching out the period it's going to take for that dough to rise. So this is really interesting kneading. So many bakers are assuming that kneading is a good thing. And the reality is that our stand mixers can often overheat the dough, and we can take kneading too far. And that this really wasn't a problem when people were making bread by hand, but when you are making dough in a mixer, things have really changed. And so this technique was developed in the 1970s by a French baker, Raymond Calvel, that was trying to combat the negative effects of the commercial mixers. And the flour and water, you basically mix the flour and water together and then just let it sit for 20 minutes before you start kneading. And we do this in the test kitchen. We actually add the yeast at that point, and we're basically leaving out the salt, but basically making the dough, mixing it together, but then not kneading it, and basically covering the bowl and coming back 20 minutes later. And what you're seeing here is these are both two doughs exactly the same. The one on the left was kneaded for 10 minutes. Basically turn the mixer on once all the ingredients were added, and you can see it hasn't really come together. This is the same ingredients. They were combined briefly let rest for 20 minutes through autolyse, and then we came back and kneaded for 10 minutes. And it's already bread dough. It's already clearing the sides of the bowl, which is the sign that the dough is ready to rise. And so basically we found that we could reduce kneading time by about 50% by using this 20-minute rest. And that the sort of negative effects of gluten getting sort of overheated and sort of losing flavor from over kneading can be combated by something as simple as a 20-minute rest. And it's really, the interesting thing is it's really related to the no-knead bread phenomenon that I think most of you probably heard about. Jim Leahy of Sullivan Street Bakery and his recipe, which was popularized by the New York Times, is really basically working on the same principle, which is that there are these proteases that are basically snipping apart the gluten strands in the no-knead bread. And that if you wait 18 hours, they've reorganized themselves, if you think of it as spilling a bunch of pickup sticks all on the counter or on the floor, and then sort of getting them all arranged in neat rows. That's basically what's happening. The 20-minute autolyse is a way to reduce kneading time and to get some of the effects of that. Yes, you do still need to knead, but if you have a stand mixer, it's fine to knead. And Dan has got a sort of little demo where he can sort of show you how that works in a more practical way.
Yeah, so I mean, I think that the no-knead bread it's pretty cool. It's kind of surprising for the people who haven't made it before. So I just kind of wanted to illustrate it. I have basically the stuff that I'm going to make a batch with here real quick. So I've got yeast, I've got flour, salt. I'm going to whisk this together so it's evenly distributed. And then I'm going to add water and a little bit of vinegar for flavor. And then I'm going to use a really great tool that you guys probably don't have at home, but you should have, and it's a dough whisk. A fellow test cook, Andrew, who's actually here tonight, turned me onto it. And it's really great because it's got just enough drag to kind of combine your ingredients, so it's a lot easier than a rubber spatula. I think this is from King Arthur. So I'm just going to stir this together. This is about the hardest part of making no-knead bread right here, stirring it. See, and then I can kind of incorporate it that way. So this is basically what you're looking for, this kind of shaggy mass. And then once that's formed, and I did this about, I guess it was probably 12 hours ago now, and I just let it sit. And so what's really cool is, I'm just going to give this kind of a turn over here. We like to turn our no-knead bread a little bit just to kind of line that gluten up. But now you can see, I mean, this has not been kneaded, and it's got a really great gluten network. Like I can bring it out and kind of get that nice window pane without really doing anything at all. So I think it's a really cool illustration to just see from this to this, just time. And what's really happening here is we have a relatively high hydration, and the fermentation is what's really forming it. So you've got bubbles moving through, and the high hydration allows the proteins and the gluten strands to kind of connect and form those nice sheets. So make some good bread.
Yeah, and it's not much work.
Not much work. No, it's pretty easy.
So I have one last case study for you, and it's sort of at the opposite end of the spectrum from bread. I mean, the funny thing is, everyone thinks bread is really hard, but bread is actually pretty simple to understand compared to drop cookies. You know, and it's like the first thing anybody makes is a chocolate chip cookie, and cookies are about the hardest thing that you can get right. I mean, they're really complex sort of chemical systems at work in your typical drop cookie. And so if we go back to where we started, I want to take you through the re-engineering process that we use in the test kitchen to change that recipe, which produces this cookies. And so we started by critiquing the Toll House cookie. And our main critiques of this were, one, it has a sort of cakier texture, and we wanted a much chewier cookie rather than a cakey texture. And it didn't really have a very sophisticated flavor. It's sweet, but we wanted more butterscotch, more toffee notes. We wanted something that was more adult and less boring. And so the first thing that we started with was the butter. And so in your classic Toll House cookie and a lot of drop cookies, you are using softened butter. And the idea is that you are beating the softened butter and the sugar together, that you're basically beating air into the butter. But the reality is that in most cookies, it's the chemical leavener, not the air that you're adding to the butter, that is causing the real rise in the cookie. And the creaming is additive, but it's not really necessary. And it's probably pushing that, and it's certainly pushing that cookie more towards the cakey end. And so if you want a chewy cookie, you really don't want to be creaming the butter. You want to be melting the butter because one, you're not adding air, which is just going to make it cakey, and two, butter is about 18% water, and by melting that butter, you make it much easier for the water that's in the butter to mix with the flour, and you get gluten development, and gluten leads to chewy cookies. So when we were doing this, though, we said, okay, well, if we're going to be melting the butter, why stop there? Why don't we take a trick from restaurants when you're having a piece of fish or you're having some vegetables that are with brown butter, with beurre noisette, and said, why don't we sort of go all the way and actually get more flavor from the butter? And that, yes, by melting it and browning it, we are getting, making the water more available to form gluten with the flour, but that we're also getting, fixing the flavor problem, which we wanted to talk about and wanted to fix. So you want to talk a little bit about brown butter?
Yeah, sure. So it's not a difficult thing to do, but there are a few tips that can make it, I think, a little bit more successful at home. And the first thing is the vessel that you're cooking it in. So I'm using an induction burner, but even if I weren't, I would still be using the skillet. So it's wide, it's silver so that you can see what's happening. Brown butter, it's all about judging color and getting out of the pan in time. So you don't want to use a nonstick pan. And you don't want to use a deep pan. My mom does it. It's like a deep nonstick pan, so it's like the worst of everything.
That's black butter?
Yeah, she makes black butter, not on purpose.
And that's not a good thing.
That's not a good thing. So that's the first thing, is choosing the right pan so that you can see what's happening. The other thing is keeping the pan moving. This is another thing my mom, I really shouldn't talk so bad about my mom, but there's another thing she doesn't do when she's making the butter. And she complains that her cooktop is completely covered in splattered butter. And it's a really simple thing to just shake the pan. So what happens is, we talked about butter being part water, right? So that water comes out, and that settles at the bottom of the skillet. You've got this layer of fat on top. So if I don't touch it for a little while, that water underneath gets really, really hot, and then it tries to escape through this layer of fat, and you get this kind of splattering like that. That was perfect timing on that.
Yeah, it's on.
It's a little bit better than the beef. So that's why you want to be shaking it early in the beginning. It looks cool, but it also serves a good purpose. Then once it starts to brown, the shaking is also important because those milk solids drop to the bottom, and that's what browns. That's where you get all that rich flavor from. The Maillard reaction that we talk about with meat is also happening with the proteins that fall out of this. And so that's going to help you keep them moving so that they brown evenly and you don't get any burn spots. So I'm going to let this go for just a couple more minutes.
You want me to start talking about sugar?
Yeah, sure.
You tell me.
See?
Oh,
Gotta keep it moving. Yeah, do you want to talk about sugar?
I'll talk about sugar
Okay,
while you continue
I'll
to brown.
keep browning. Talk about sugar.
So one way we fixed, we sort of improved the Toll House cookie recipe was obviously by, rather than creaming the butter, browning it. The second thing we looked at was the sugar. And that, most people think of sugar as providing sweetness, but sugar actually is hugely important in terms of determining the texture of any baked good, and especially in a cookie. And the main thing you need to think about is that sugar has an affinity for water. It's hygroscopic. And the sugar also will sort of slow the evaporation of moisture in a baked good. And so, if you leave out the sugar, besides it won't be very sweet, it will
Jack,
be really
I gotta
dry.
jump in. Sorry, I gotta
look
jump
at you.
in. So it's important to get brown butter out of the pan when it's done, or even a little bit before it's done, because it's going to continue to cook. There's a lot of heat in it, and so in order to have brown and not blackened butter, you need to get it out right away, or stop it in some way by adding liquid to the pan. So this will continue to get a little bit darker. But you can smell it. It smells pretty good, and that provides a lot of the flavor for the cookies that you guys are going to get to taste.
Yeah. This is another test kitchen experiment that Dan ran, where he took the exact same cookie and made it one with brown sugar and one with white sugar, and then tried to mold them when they were cool around a rolling pin. And besides obviously getting a different flavor from using brown sugar than white sugar, you actually get a different texture. The difference is that you get a much chewier cookie, one that can mold around a rolling pin when you use brown sugar, and on the right, we were using white sugar, and you get a cookie that is much crisper and not as chewy. And the difference is the granulated sugar is pure sucrose, and the brown sugar is sucrose with some invert sugar in it. Now, invert sugars are basically liquid sugars, so think molasses or the molasses that's in brown sugars. And they have a really hard time crystallizing, unlike sucrose, which obviously forms really nice crystals that we all know as granulated sugar. Invert sugar actually holds onto more moisture than sucrose. It can even draw in moisture from the air once the cookie is finished baking, and will keep a cookie made with brown sugar chewy longer than white sugar simply because it's drawing in more moisture from the air. Now, the classic Toll House cookie is made with equal amounts white and brown sugar. So first thing we did was that let's use 3 parts brown sugar to 2 parts granulated sugar to sort of increase the amount of invert sugar. We actually tried going further, but we felt like the cookies were too soft, and they were almost floppy. So in addition to changing the ratio of brown to white sugar, we also treated the sugar differently. Now, when sugar is dissolved in liquid, before baking, it's going to caramelize much more quickly and much more easily in the oven. And so for our perfect chocolate chip cookies, we let the batter rest for 10 minutes before we formed the balls of dough. We'd actually seen recipes that said, let the dough rest 24 hours. We found that 10 minutes actually got us enough of the sucrose basically dissolving in liquid ingredients, the melted butter, the vanilla, and the eggs, and that those dissolved sugars, they would caramelize at a lower oven temperature and faster. And so, more caramelization led to more flavor, more of the butterscotch and toffee notes. And additionally, those super caramelized edges, when the cookies cooled, they got these really brittle edges. And so you had this really nice contrast between a crisp, almost brittle edge and a chewy center. And so Dan has 2 doughs.
I do. So this is probably pretty familiar to folks. This is the Toll House dough, which we're really trashing tonight.
Yeah.
We're really not supporting the Toll House cookie. It was a good starting place, but as you can see, so it's lighter in color. That speaks to the sugar that we talked about. It's got a lot more white sugar in it than our recipe does. We're also not browning the butter; it's creamed. But you can also see that it has kind of a matte finish to it. And in contrast, this is our cookie dough. If you can see up there. So it's obviously a lot darker. It's got the brown butter. It's got more brown sugar, but it's also kind of smooth and shiny. And that really speaks to not only the fact that we melt the butter, but also these dissolved sugars. So we've got more fructose and more glucose. Those react, in the Maillard reaction a lot faster, so you get more flavor, you get more of those crispy edges. So you can even see it here, and you'll get to taste it as well.
So in addition to butter and sugar, one of the biggest effects on any cookie is going to be the chemical leaveners. And so baking soda and baking powder are often used singly or in combination in pretty much every cookie recipe that you will find. There are a few exceptions, but most cookies, including chocolate chip cookies, contain one or both. Now, baking powder is simply baking soda. It's roughly 1/4 to 1/3 of the total is baking soda that's mixed with a dry acid, such as cream of tartar, and a double-dried cornstarch, which basically keeps them separate. And when it hydrates, the acid and the baking soda combine, and you've got CO2 being produced. A single-acting baking powder has 1 dry acid, and double acting has 2, usually one of them being heat sensitive. And so baking powder, you get generally more rise from baking powder than baking soda, because it can continue to work in the oven, and that when you use baking soda, you generally get a bit less rise than you do with baking powder. Many cookies have both leaveners in them. We found that we really just needed the baking soda, and that the baking soda, in addition to sort of eliminating the baking powder, which was giving us too much rise and giving us almost like a cakey texture, the baking soda is really great because it also causes browning, and browning is going to lead to flavor development. And the really interesting thing there is because browning occurs best in an alkaline environment, and amino acid molecules, like those found in flour, have two ends. They have an amino end and an acid end. And the acid end is acidic, and the amino end is alkaline. And it's the alkaline that has to react with, the alkaline end rather, that has to react with the sugar molecules for the Maillard reaction and the browning to occur. And in an acidic dough, the alkaline ends are deactivated, but in an alkaline dough and something that's made more alkaline by the addition of baking soda, the amino acids thrive, and they react with the sugars to create browning. Baking soda also encourages spread. It raises the pH of the dough and sort of weakens the gluten development. And so the more spread you get in the cookie, the chewier it's going to be. And that if the dough balls don't spread very much, they end up baking up sort of taller and more cakey rather than chewier. The other variables, besides, in terms of the ingredients, besides the leavener, would be the egg, and we ended up using the yolk rather than a whole egg, and the type and the amount of flour. We got rid of the egg white because it kind of, again, creates more structure and more cakiness, and that we wanted the fat from the yolk, but we didn't necessarily want the structure from the proteins in the whites. So in addition to sort of re-engineering the ingredients of this, I just want to come back to a couple of sort of the variables that we talked about in the beginning. We used a couple of techniques in the recipe in order to ensure good results. So here is an example of us putting in a tray of cookies and leaving them be. And if you notice, the cookies in the back are browner than the cookies in the front. And that's because every oven has hot and cold spots. So every single cookie recipe that we ever develop at America's Test Kitchen, we switch the position of the baking sheet 180 degrees. So halfway through, the front becomes the back, and the back becomes the front. In addition to doing that rotation, we need to think about the positioning of the cookies in the oven. And so this is a good example of the difference between two cakes that are stacked one on top of each other, one on the top rack, one on the bottom rack, and versus two cakes that are put side by side. And the point here is that when you stack two cookie sheets on top of each other, you need to switch the positions of those racks at the halfway point, the baking sheets rather. And so the one that's on the top needs to go down to the bottom, and it needs to turn 180 degrees, and the one that's on the bottom needs to go on the top. The easiest way to do this is to just do one baking sheet at a time in the middle rack, and so you don't have to remember to sort of do that juggling. But it comes back to your oven can be your friend, or your oven can be your enemy. Last one is equipment. I mean, it wouldn't seem like this would make a big difference, but we found that the material of your cookie sheet can make a big difference. The darker the sheet, the faster it's going to cook and the more browning you're going to get. In this case, the sheet on, these are both cooked the exact same amount of time, same temperature, same oven, one after the other. And you see that without the rims, you get sort of better airflow and you get more browning. And that these on the right, which is on a rimmed baking sheet, are really probably needed another minute or two in the oven to be done. And at the same baking time, they're less done simply because of a rim this big. And so, these teeny variables can have a relatively significant effect, and which is why when you're following a recipe, often it doesn't seem to be actually working just right.
Right.
So I want to thank you, and you will be getting a cookie after the Q&A.
True.
But I really wanted, I hope that this talk has encouraged you to think about how you can apply science in your own kitchen. I would really encourage you to go watch, there are 4 great videos on this website, cisciencebook.com, where you can see Dan do experiments in our test kitchen. And Dan's really quite funny. He's funny here, but he's really funny in these videos.
Yeah,
and
less
they're
funny.
really, really interesting. And there are 4 videos there that you can go watch, sort of see Dan at work in his natural environment.
Yep.
So I want to thank you, everybody.
See, I told you they were scientists. You didn't do a very good job convincing us you're not a scientist.
I'll try harder next time.
Okay, so we have some questions, and then after questions, you all get cookies, and then you can go outside, and there will be a book signing. Yes.
Thank you so much for coming. This was really enjoyable. So you're out looking for the best way to do something, and best is obviously interpreted in various ways, but you're out looking to do the best of something. Have you ever encountered situations where doing the best deviated from the most enjoyable?
Yeah, anytime you have to do dishes. We were talking about this over dinner, that I feel like the greatest flaw in the way that we have organized our company is that rather than the people who have to develop the recipes doing their own dishes, we have 3 full-time people who do the dishes for you. So, you know, often best causes those problems. But I don't know, Dan, do you? I mean...
Not necessarily enjoyable, but flavorful.
Yeah.
Yeah, I mean, I don't know, speaking, I guess to Jack's point, in terms of when we do recipe development, we send our recipes out to the public to also test them. So we get a lot of feedback from people as to whether what we're tasting in the kitchen is translating, and you know, if our recipes are kind of a pain, like there's too many dishes, they'll kind of tell us that sort of thing. But I guess I don't quite understand your point about best versus it's not.
Well, I guess you answered it by saying that you're defining best by being interpretations of what people are liking.
Yes, yeah, and I definitely think as a group, you know, America's Test Kitchen as a group, and we're all tasting together, it's definitely our interpretation of best, but we do a lot of reality checks kind of with the public to make sure that that's really checking out.
Do you have a diversity of palates in your group?
I think we do.
Like origins, where people come from?
Yeah, I would say so.
Yeah, and I think the other variable that goes into our formulation of best is how reliable and how foolproof it is. And the thing is, we've often developed recipes that if you do everything exactly right, it will come out fine, but the sort of tolerance for deviation is relatively low. And when we send a recipe out and we'll get 100 people to make it and send us back reports, we can sort of see that, you know, 40% of the people making this recipe are having absolute disastrous results. Well, that's not really acceptable for, you know, what it is that we're trying to do, that it has to be replicable in order to also be best. And that sometimes we end up making, you know, some compromises, I think, along the way in order to get a recipe that will actually work for the vast majority of people and, you know, work with some deviation from ideal protocol.
So question right here.
Hi, thank you. When you were describing reproducibility in the home kitchen, you talked about an experiment where you had several people measure a cup of flour or a cup of water, and I found that experiment interesting. I was wondering if you had done a similar one where you had the same person measuring a cup of flour several times to see what the deviation was there. In other words, how often can I blame that on my failure?
Yeah, I mean, the interesting thing is it's all about the amount of force. And, you know, unless you're a machine, even the same person is going to sort of get more or less force and therefore more or less flour packed into it. Now, there seem to be some really aggressive flour dippers, and, you know, some less aggressive that accounts for some of the variability. But even, yes, I mean, if you were to do that test yourself, you would see that you would not have the same amount of flour in the cup each time. And the same thing when, I mean, I have this, if you use a measuring cup, it's like, well, where exactly should you be measuring to, when you're measuring a cup of water? And that, that's why weighing is really the way to go, if you can.
Question right here.
Thank you very much. I'm wondering what you would suggest for us to buy to calibrate our ovens.
An oven thermometer.
Are those reliable? Any particular kind?
I think our top rated is it the OXO?
I don't remember if it's the OXO or the Taylor. Yeah, we tested those as well. So we have a winner that is definitely good. and we use that to calibrate with.
Yeah. I want to say it's either Taylor or OXO. I don't know. Taylor. Andrew's saying Taylor.
Taylor?
I think they're about $15. I mean, you can always test them by like putting it in some ice water or putting it in boiling water. Probably ice water would be better. But if you have any doubts, but we haven't had any real problems with reliability. And the thing is, you don't need an oven to be. If it's 354, it's fine. I mean, the problem is if it's 400 and you think it's 350, and any decent oven thermometer is going to tell you how close you are. And the thing is, you just put it in there in the middle rack, leave it alone, let it go for half an hour, and then see where you are. I mean, naturally, your oven is going to cycle up and down, and even by design, an oven that's set to 350 likely during the course of baking will vary between 340 and 360, because what happens is the heating element turns off once the oven gets up to 360, for instance, and when it cools down to a certain preset temperature, it'll then turn back on. And so 10 degrees is not the problem. The problem is when you're 50 degrees off, because then you're going to be burning a lot of things or underbaking a lot of things.
I have a question right there.
Yeah, you mentioned cold butter in one particular recipe, and I'm just curious why cold butter versus, I don't know, room temperature butter?
Cold butter. Was that in the omelet recipe? The omelet recipe? I think the reason that we do that is it disperses better in. So, like as the eggs are cooking and as they're unraveling and starting to come together, that butter is then dispersing at that point. I don't remember the exact details of why we did it, but I'm pretty sure that's what it was. It just worked out timing-wise really well for right when that protein bonding was taking place. The fat was there to kind of take over.
And I think in that omelet recipe, the butter was actually, I think, in the freezer for a couple of minutes.
So
you cut it into really teeny cubes. I think there's a tablespoon in an omelet, cut into teeny cubes. And I think the idea also is to get that fat to melt more slowly and to be adding its protection throughout the entire cooking period. I think it also is it's easier to disperse and it won't clump together. If you have these little teeny cubes that you've put on a plate in the freezer for 10 minutes, you'll get them more evenly dispersed than if you just throw in a 1 tablespoon hunk.
Is there a question right here? Here, wait, get the microphones.
Thank you. I'm curious about sugars. And you talked about white and brown. And then there are sugars like granulated, which I haven't been able to read much about, but I personally like because it doesn't get hard the way brown sugar does. But there are also things like some of the more natural sugars, and I wonder if you could talk about them a little bit.
Yeah, I mean, I think the easiest summary that I can give about all of the sweetener world is that the textural differences are generally bigger than the flavor differences when you start. People always ask me, can I bake with Splenda? It's like, yeah, you can bake with Splenda, but you're going to have really dry brownies. And they may be sweet, and they may taste totally fine, especially if you've got a lot of other strong flavors in there. But whenever we do any tests where we're sort of combining, comparing different baked goods made with different types of sweeteners, I always think the texture differences are much more apparent, and that it's generally, that they're dry, they're crumbly, and they don't seem, as moist as they should be. I don't know, Dan, if you have any sort of further thoughts on that.
Yeah, no, I mean, I think that kind of speaks to it. I know some of the more natural kind of sugar in the raw, that sort of thing, they're going to have, more trace amounts of those reducing sugars like fructose and glucose, but it's not in a controlled kind of way that it is with brown sugar. Like with brown sugar, we kind of understand how it's going to work, and I would kind of be curious about how raw sugar, like how much is actually in it, and from batch to batch, or different brands. So we tend to kind of stick to the stuff that we know. And the granulated, I've seen that too. I don't know that a whole lot about it. I don't think we've done much testing with it.
Yeah, I don't think that behaves all that differently, the granulated sugar. And I think and the biggest differences are in cakes and cookies. If you're making a pudding, obviously the sugar is mostly at that point supplying sweetness, not really such a big determinant factor in texture.
Yeah.
It may affect color, but that's a whole other issue.
So maybe we'll take one last question. This is because you can be the last question, just because there are cookies and there's book signing, and I don't want to.
Because they're cookies.
They're cookies. They're cookies. Well, it's not only cookies; it's cookies from that very brown dough.
I was wondering if you've tested saltiness with water and oil, and if it makes any difference with salt. You said that it's better to add spices to oil. Is that true of salt?
I'm sorry, I don't understand the question. Can you
Or
repeat it?
you said that you tested adding spices into water and into oil. And I was wondering if that includes salt.
Yeah.
No, we did not. No, so we worked with mainly spices and herbs that have either a water or oil soluble flavor compound in them. So salt wouldn't really fit into that category. So no, we didn't. We do a lot of stuff with salt, but we didn't do that test with it.
And salt is, I'm not sure calling salt water soluble is actually right, but salt can penetrate foods. I mean, unlike the fat soluble compounds in a lot of spices and herbs, where meat, most protein is 75% water, and so it's going to repel fat. I mean, at the simplest level. And so that's why those compounds have a hard time getting into, if you're hoping to get the flavor of cumin inside a steak, it's really hard to do. Salt, because it, of osmosis and diffusion, will actually get into meat. It's really just a question of time as to how far in it will get. And so salt really behaves really quite differently than most of the other ingredients that are in a marinade.
Okay, so I'd like to propose that we all clap. And so I'm not exactly sure how this works, but I believe that if you are on this side of the room and you go out that door, and if you're on that side of the room and you go out that door, you get a cookie. This is what I believe. I'm not entirely sure, but that's what I was been led to believe.